Markov chain has 2 to the n states. So we're going to think of the states as words of blacks and whites, B's and W's. And there's certain transition probabilities, namely, you think of these as particles that can occupy n different points linearly on a line. And you think of a particle possibly moving to the right, moving to the left, exiting from the left, entering from the left, or exiting from the left, or entering from the right. You know, these transition probabilities with U, Q, alpha, beta, gamma, and delta there. These 6 parameters. It's the asymmetrical exclusion process. What does this have to do with Askew-Wilson polynomials? We'll put U equal 1 for the statement of this theorem. Although we don't have to have that, but we'll just state it like U equals 1. Here's a theorem of Corteil and Williams that says, take a state W, that would correspond to some kind of word of B's and W's. What's the probability of W in the stationary distribution of this Markov chain? What's the probability you're in that state? It's going to depend in some way on these transition probabilities, alpha, beta, gamma, delta, and Q. Their theorem is, it's a quotient of polynomials in those 5 parameters. The polynomials all have positive coefficients. And in fact, the polynomials can be described completely combinatorially. The numerator polynomial is just taking a certain subset of the denominator polynomial's terms. So the denominator is the sum of all the numerator ones. That's the partition function of the entire Markov chain. What are the things you're summing over? You're summing over things called staircase tableau. So there's some way of making a complicated tableau a staircase shape. The number of these tableaux is this 2 to the 2n times n factorial. That's the number of terms of the denominator. N factorial times 2 to the 2n. So you can think of that as like a signed permutation paired up with a word. It would be like 2 to the n factorial times 2 to the n. You can specialize these other parameters to get perfect matchings or permutations by specializing again in the delta. Let's slightly generalize this partition function by counting how many particles you have, how many B's there are, how many blacks there are. So take the generating function according to the number of particles also. So Z equal 1 would be the partition function. So here's one of their theorems. The nth moment of the Askew-Wilson polynomial is exactly this partition function. But you have to put y equal to -1. The Askew-Wilson polynomials do not have positive coefficients when they find their moments. You have to put y equal to -1. And you have to do this rather amazing Catalan type change of variables from the alpha, beta, gamma, deltas to the A, B, C, D. The strange Catalan change of variables. I don't understand that at all yet. Why that is. So this means that any of the formulas you have for the Askew-Wilson moments now immediately apply to the stationary state problem of the asymmetrical exclusionary process. Any questions?
Do we have an independent book? And so does it imply what Corteil, what the Doron will see, but it's more general? Do you have a new book?
No.
Or no?
I don't have any proofs of Doron.
So why does you have?
That's not my theorem, that's their theorem.
Oh, yes. So they use that.
I'm using their theorem, yeah. I'm just telling you about their theorem. It's really
But then
good.
you're about asking Wilson, or it's your formulation?
No, that's their formulation. In fact, originally it was due to some physicists, but we had to massage it a bit to change it into this. They didn't have exactly this, but they basically had it. Any questions for the first part of the talk? Identities.
I have a comment. The case when gamma equals delta equals 0 and q equals 0 was one of the first papers of Shapiro and Zeilberger.
Yes. Okay, second part of the talk. Inequalities. So as Doron's already said today, inequalities are more difficult than equalities. And I would really be happy if there's some automated way of proving inequalities that I can't do. There's a lot of those. Let's take a very simple example of the q-binomial coefficient, n choose k base q. This has two combinatorial definitions that I've written here. The first one is the generating function for partitions inside a rectangle. And the second one is when q is a prime power, the number of k-dimensional subspaces of an n-dimensional space over a finite field. The first one, q, is a generating function parameter. The second one, it's a prime power. Let's just remind ourselves why this is true. Basically, if I had, for example, a two-dimensional subspace or a five-dimensional space, I could take a basis of that two-dimensional space and write it in row echelon form with leading ones. And these stars represent arbitrary field elements. So you do get a partition inside a 2x3 rectangle. So Herb knows this very well. Q-binomial. Here's a very simple inequality involving q-binomial. Let's define n choose k prime to be a certain minus sign times n choose k negative q. I'm going to replace q by negative q and multiply by a sign that basically means the leading term is positive. It's pretty easy to see that this prime thing is trapped between 0 and the unprime thing. The good question would be, which subspaces, which are counted by n choose k, are counted by this n choose k prime thing? There's some subset of subspaces. What are they? We figure out what they are. Yes, we can figure it out. It's a little complicated here. Basically, it says you take certain partitions which lie inside a box, and certain ones of these stars have to be non-zero. So you're going to restrict the partitions you have, and you restrict certain stars to be non-zero. So this is going to mean there'll be an expansion in terms of powers of q and powers of q minus 1. Restricting to be non-zero means there's q minus 1 choices. Okay, let's not look at the exact details of what that thing is. So let's write down the formula. Well, let's do an example maybe first of all. Here's an example. If you take 2 and 5, you get to these partitions which have at most 3 parts, largest part is 2, and the little arrows there point to particular field elements that are non-zero. So there's q minus 1 choices for those. So if you add up these 6 possibilities, you get 5 choose 2 prime. Notice 5 choose 2 equals 10. There's actually 10 total lambdas inside the box. Only 6 of them appear here. So you get a subset of the lambdas, and the lambdas have smaller weight. You explain completely which subspaces are counted.
But this is valid for every power of p.
Yes.
When you write this, so this is valid for every.
Okay. Even though I did it for a field element, it's true for any q whatsoever.
So it's positive. Because
And they're polynomials, so it's always true. So here I've written down the exact formula you would get for n choose k prime. Instead of summing over all partitions inside a box, the power of q, you get a power of q times the power of q minus 1. The sum of those powers is the same old power we had before. It would be the inversion number of the permutation, or the number of cells in the Ferris diagram. But what this looks like is, in this Grassmannian cell we have for this Planck complex, certain affine spaces stay affine, certain other affine spaces get punctured, and certain cells are completely deleted. That's what this is saying. So this sounds